So I'm going to be walking through question 6 of round 1 of the Maths Teams Olympiad. So this question is quite nice. It's a fairly straightforward number theory problem, and it's the first of the long style questions. So this should be fairly simple to do, and it's just to get the teams a taster of what the style of answer should look like. I'm not going to write a full-out rigorous proof to this. That is left for the viewer to do if they're bored enough, but I am going to give an outline of the proof, basically. So if we just if we have a 2-digit number and we have the first digit be alpha, and the second digit to be beta, and we can write this number alpha beta with a dash over it. This form is exact same of saying it's 10 alpha plus beta. So the tens digit is the alpha and the units digit is beta. So there's 10 lots of alpha and a beta, and this is for alpha and beta are in this range where alpha cannot be 0. It's a bit of a weird inequality, but that's the way I could think about to write it like that. So if we have 2-digit number and this number is a full and isomer number, then it will satisfy this condition. It will satisfy the condition that 10 alpha plus beta is equal to 13 times alpha plus beta. As we can see, moving on, this is equivalent to 3 alpha plus 12 beta is equivalent to 0. However, from our restrictions on alpha and beta being between 0 and 9, unless alpha and beta are both 0 and alpha is not allowed to be 0, then it's pretty clear to see there's no solutions for positive numbers of alpha and beta equal to 0. We may note that if we make this our list over here of A numbers, here is the set, we can add 0 because 0 is a full and isomer number, but it's not a positive a positive integer, so it doesn't count. So we can't say the case when alpha and beta are both 0, that does not count. So that's proved that for 2-digit numbers it is impossible. There's definitely space to add more rigor and more mathematical firmness on this argument, but we don't have the time in this video. So if we try for the 3-digit case, where it's going to be like alpha, beta, gamma, and we can represent that as 100 alpha plus 10 beta plus gamma, then the full and isomer number will satisfy this condition here, equal to gamma, and this is equal to 13 times the sum of alpha, beta, and gamma. So you can see moving some terms out and expanding. If we get this side, we've got 13 alpha plus 13 beta plus gamma, and we can move these terms over to the left here, or let's just move the 13 alpha, so then we get 87 alpha, and then 3 beta, and that should be a 13 gamma there, 13 gamma, and this is going to be a 12 gamma here. Then we've got this equation, 87 alpha plus 3 beta equals 12 gamma. I thought 87 was a prime when I first tried this problem, but I discovered it's not prime, which kind of scared me. So if you divide 87 through by 3, you get 29 alpha is equivalent to beta plus 4 gamma. Using the fact that alpha, beta, and gamma all lie in this range of 0 to 9, then it's fairly simple to see that the maximum of the right hand side is when beta is equal to gamma is equal to 9, and 9 plus 4 times 9 is 5 times 9, which is 45, and that means the right hand side has a maximum of 45, and the left hand side, in terms of alpha, well, if alpha is 1, then the left hand side is going to be 29, but if alpha is 2, that's going to be greater than 45. So for a 3-digit Folland Eisenhower number, the first digit, which is the alpha, can only be 1. So we know the number must be 29 equals to beta plus 4 gamma. And I'm not going to go through all the cases and how you do this, but there's trial and error, and you would eventually find cases fairly simply. I can see one off the top of my eye. Beta equals 1, gamma equals 7. That's a case. So 1, 1, 7 would be a Folland Eisenhower number, and you would go on doing that to find the rest. Well, it asked to find with proof all Folland Eisenhower numbers, and we've only proved that there's none for 2-digit numbers, and there's a finite amount for 3-digit numbers, which in a full solution would find them all. So let's just hop on to 4-digit numbers and find out why there can be no 4-digit numbers. So if we let the 4-digit number be alpha, beta, gamma, I don't know what the fourth Greek letter is, but let's just say theta. If that's our number, then it's going to be 1000 alpha plus 100 beta plus 10 gamma plus theta. I know that's going to annoy you a lot, but I'm sorry, I don't know many Greek letters. So we can say if this is a Folland Eisenhower number, it will satisfy the following condition. That 1000 alpha plus 100 beta plus 10 gamma plus theta is equal to 13 times the sum of alpha, beta, gamma, and theta. If we see on the right hand side, the maximum of this expression is when alpha equals beta equals gamma equals theta equals 9. This is going to be 9 times 4 times 13, which is equivalent to 468. So the maximum of this right hand side is 468. However, if you look at this left hand side, well, as alpha has got to at least be greater than 1, so it can't be 0, then the left hand side will always be greater. So we can say alpha, beta, gamma, theta will always be greater than 1000. And you can do more stricter inequalities, but it's simple enough to show that the right hand side will always be less than 1000, and the number will always be greater than 1000. So it proves for no 4-digit numbers, no Folland Eisenhower numbers exist. Like I said, you could go in with more rigor and more mathematical structure and firmness, and a complete proof would require that, but this briefly goes over the solution, and I'm pretty sure you guys would know how to finish it from then on. But yeah,